Lesson 11:11, Polarization. Linearly polarized light vibrates in only one direction, just up and down or just sideways. Common light, non-polarized light, vibrates in all directions perpendicular to the direction of travel. So the light is bouncing. So like if it's polarized, it is only going one way. What's non-polarized is going that way, but it's also going in and out, in and out, and at angles, and front and back. It's all over the place. Whereas if it's polarized, it's all the same direction. We can polarize light by using things like broadcasting with a straight wire antenna. It's just up and down along the antenna. Reflections off flat surfaces. That's why you get polarized sunglasses. Or passing through a polarizing material. Polarizing materials are ones that allow light to be polarized only along the transmission axis. Usually it's a material made out of long chains of molecules or something like that. All components of the wave are absorbed except the components parallel to the transmission axis. So light's coming in all ways. There's like this little gate. Think of a fence. I'm sure you've seen these little picket fences. So the light can only go up and down between them. Can't go side to side. Everything side to side gets absorbed. Since unpolarized light vibrates equally in all directions, when we polarize it, half of it's gone. So in this case here, the Y components are transmitted, the X components are not. So since half the components are gone, our intensity is 1/2 the original intensity after it goes through a polarizing material. Malice's law tells us the formula for calculating how much light gets through. After light has been polarized, a second polarizer can be used to adjust the intensity of the transmitted light. So we start off here with unpolarized light. It goes through this polarizer, and that's its transmission axis. And then we have another I know it says analyzer, but it's just another polarizer. It's the same thing. It's just at a different angle. So now the components from the first thing now have to go through that angle, so some of it is absorbed, and you end up with less light. The polarizer polarizes the light. The analyzer polarizes the polarized light along another axis. It will only transmit the component parallel to the transmission axis of the analyzer. And the formula to figure out the intensity of light after the analyzer is I equals I0 cosine squared theta, where theta is the angle between the two polarizers, or between the polarizer and the analyzer. There are many uses of polarization. First of all, sunglasses. Light reflecting off things like roads and windshields and the water are all polarized one way. So if you have polarized sunglasses, they polarize them at 90 degrees to that, so it blocks much of the light that's being reflected off of the surfaces. Because if you go back to Malice's law, cosine of 90 degrees is 0. So it automatically cuts light intensity in half, and it blocks the polarized light that's reflected off water, roads, windshields, etc. You can use polarization to make 3D movies. You have two cameras. They're side by side, but they're projected with two projectors side by side, but polarized at 90 degrees. So one side let's say, is going up, the other eye is that way, and then you wear these little glasses that are polarized the same way. And so the left eye only sees the left eye, and the right eye only sees the right eye. And it looks 3D. LCD, liquid crystal displays. That's like the display in your phone, probably, or your calculator. Voltage changes the direction of the polarization of these liquid crystals. And the pixels are turned on, are transmitted. They're parallel to the polarization axis. The pixels that are turned off are perpendicular to the polarization axis, and they just look black. A certain camera lens uses two polarizing filters to decrease the intensity of light entering the camera. If the light intensity in the scene is 20 watts per meter squared, what is the intensity of the light between the two filters? All right, so we are looking for, in part A, this first question, what is the intensity right there after the first polarizer? Well, after it goes through one polarizer, its intensity is cut in half. So it was 20 watts per meter squared, so now it'll be 10 watts per meter squared. So this is now 10 watts per meter squared. This was 20 watts per meter squared. Now, if the light intensity at the film is 3 watts per meter squared, what is the angle between the transmission axes of the polarizers? So we are going to use these two, this one and that one, in Malice's law. So this would be I0, and this one is just I. Plug those in, divide by 10, take a square root, and then inverse cosine, and you see your angle between the two polarizers is 56.8 degrees. All right, I've been telling you that things reflecting on a flat surface, that light can be polarized. The light will be polarized perpendicular to the surface is more likely refracted. Light horizontal to the surface is more likely reflected. Light is completely polarized at Brewster's angle. And that is found tangent of the angle equals n2 over n1, where we have Brewster's angle and the indices of refraction. And I don't have an example on that, but yeah. Have a good day. End of the unit.